Okay, so hello everyone, and thanks for joining today. So today, let's start again. What did we talk about this class? We talk about, some important problems for networks. Then we talk about embedding into trees. We talk about different approaches. We talk about planar graphs, H-free graphs, and essentially sparse graph in general. How can we also simplify them and then generally embed them in some sense to the bounded Trivets graphs? We talk about large graphs. How can we handle it? In particular, we talk about streaming algorithms. I mentioned there are also MapReduce that you can see it in my introduction to algorithm last session. There are some that we talk about it, and probably we will talk more later. Here, I want to talk about another, two super important problems for networks. Almost no network you can work on it if there is no kind of clustering algorithm. And this another interesting thing about clustering is that clustering actually, I will say, to some extent, I can say the whole, if you do essentially machine learning, so unsupervised machine learning is essentially clustering. So that's probably one of the most important things. And here there are two very important things about the theoretical thing that I want to mention. And actually there are some interesting open problem for a long time that still is open here. Good. So let's start. So two problems that we want to talk about it. Here is the K-center problem, and the other one is K-media. And this is interesting. Generally, there are K-center. These are two important things. This is essentially max versus average, or essentially sum. So these are the things that almost any optimization function that you work on it, you can think about max objective function versus the like essentially average. And average and the sum are the same because you just factor n away. And these are the two important things that we want to talk about for clustering. So what is the things that we want to do is, so in the K-center, so you are given a network and an integer K, and this is some distance essentially function for any two thing. Essentially the distance function, we are assuming a metric things between any two vertices. It can be like essentially in some Euclidean space or two-dimensional, three-dimensional, etc., but it can be essentially general. And then you want to find a set X of exactly K vertices such that this is the objective that for K-center. You want each vertex, what is the D of V and X means that essentially the distance between a vertex V and, so in general, D of V of X means that the who is the closest vertex in X to V and that distance. So if this is X, for example, and this is V, so here, for example, if there is this vertex, there are lots of vertices here. This vertex essentially is this V prime in X, and this distance essentially would be this. So the distance of a vertex to a set means that find the closest vertex in that set to this vertex and take the distance. That's essentially the definition of K-center. So you try to essentially find K-centers. And this you want to maximize okay, and you want to minimize this maximum. So the objective is to minimize this maximum. So for each vertex, find essentially like for all vertices, you will see who is the closest guy. You will find the maximum among all vertices, and you want to minimize that maximum. What about, this is K-center, what about K-median? The K-median is that instead of doing that, you just want to essentially minimize the average distance. So you want to minimize the sum of this D of Dx. And again, sum and average are the same. You can divide everything by this. You can just divide it by size of V, but this will be same. And this is always the case when you try to, anytime that you have the max, almost the same time you have the sigma, should consider it. These are both interesting, and almost all of them are non-trivial. Sometimes actually, I will say the max is harder. In this case, actually, the sum is harder. And so what is the problem here? Essentially, these are the things you want to, you want to select K centers. The number of them should be K. This guy should be K. Such that either you want to minimize the maximum distance of a vertex to closest eye here, or you want to minimize the average or sum of the distance, each vertex to this K centers that you are choosing. It's very natural. And why is it clustering? Because always you can assign this vertex to the closest, essentially, you can consider this X as a center, and each vertex will be assigned to one of these centers. So that's essentially the way, there's a very natural way of clustering. Each vertex go to the closest guy, and then you try to optimize some objective function for this clustering. Very famous sort of problem, very important. Now, what do we know here? So let me just clear everything. Good. The first thing is that for this problem, for the K center, so we will talk first about K center. The algorithms are simpler in some sense here. And then we will talk about K media. So the first thing is that we can, this is again, this is always, when we say that we are guessing the optimum, this is a typical thing that we are seeing in network design and others. It means that, I mean, we can consider all possibilities. So here, what can be the optimum? The optimum can be at most, like if you consider n choose two possible pairs, the distances between them, optimum is one of them. Because anyhow, you can consider one vertex to a distance, the distance of one vertex to another set, which will be distance of this vertex to a set, to a vertex in that set. And there are how many pairs do we have? N choose two. So optimum is one of them. And of course, you can try all of them, or you can do binary search if you want. So that is, again, typical thing that you can consider binary search, and then one of them would be the solution. So here, assuming that, but the question is that I guess, of course, they said this is the optimum. The issue that can you find a solution of that cost or approximate? So this is the things that we want to use it now. Assume that this delta is the guessed optimum value. Again, we don't know whether it exists. We need to check it. Now, here I want to give, for this K center, I want to get a two approximation for K center. And then we say, actually, we know that two is tight, at least until some complexity. So how can we do that? So consider an auxiliary undirected graph, G delta, in which two vertices U and V, they have an edge to each other if the distance between them is at most. Good. So this essentially consider the whole graph. This is the G. And then create this auxiliary. This is G is the metric. There are weighted edges. Here, this is undirected essentially. So consider an auxiliary undirected graph. And then the first thing is that the optimum solution forms the dominating set in G delta. Why? Because, I mean, just consider this vertices. This is the optimum, guys. So optimum, guys, I mean, any vertex should be, these are the K guys here. So these are the optimum, essentially. This optimum, the number is K of them. Each vertex should be at most delta to one of them, but that's by definition of that. So if consider this one, any vertex either is in the set or one of its neighbors. So that's a dominating. Now, this is important. this is the power of an undirected graph. So this power actually is the important one. So what is the power? So this is the graph. So consider a positive integer c, generally constant. Define hc, that there is an edge between two vertices if and only if the distance between them is at most c. Good. So, like for example, if you consider if this is G, these two vertices are so these two vertices, they essentially X and Y are connected. Now, in the G prime 2, also this other edge. So not only these edges are connected in G prime 2, but also there is the edge between. That's also, so these power graph are important. Actually, this for power graph, also when we talk about bidimensionality, etc., lots of them can be generalized for the powers of planar graph, powers of H-minor field graphs, etc. And why powers are important? Because in the general, the thing that happens is that these graphs are sparse, like planar graph, H-minor field graphs, etc. However, power graphs are not sparse anymore. They have a large clique because if you have just a star here, in the power graph, everyone will be connected to each other. Just if you consider the power of 2 of the graph, essentially a neighbor, all the neighbors of a vertex will be connected. So if the degree of a vertex is n, or then we have a clique of size. So these power graphs are important because these are generally dense graphs that can be still solved using some approaches of, for some of these graphs, these are the power graphs of planar graphs. Even though they are dense, we have a good algorithm to solve them. So power graphs are something that can be here. But that was some kind of thing I wanted to mention why power graphs are generally very important. But power graphs plays an interesting role here. So let me just finish this one. Good. So this is the lemma, which is actually interesting. It's simple. If X is a dominating set in G, in the power graph, in the power G of delta to the C, for some positive integer C, and the size of X is at most K, then X is a C approximation for K center form. That is easy. Why? Because if it is a dominating set, then it means that why it is a C approximation, it has C times delta, because each vertex from the graph is at distance. So if these are like C approximation, if there are the GC, it means that any two vertices in GC is, so if this is like delta, this is delta, this would be at most 2 delta. So if you have a dominating set here, then and the size is at most K, every vertex is at most C delta from these people in the original graph. Because in the power graph is a dominating set. It means that each vertex should be essentially either in the set or adjacent to some other vertex. But it will be adjacent to some other vertex if the distance in the original graph is at most C times delta. So it would be C essentially approximation for the. So that is important. So G to the C and then C approximation. What should I do to show a two approximation for the problem? I need to find a dominating set in G delta to the 2, just squares, that its size is at most K. Good. And there is no need to be optimum dominating set. As long as I can guarantee that the size is at most K, I will be fine. Good. So how can we solve this one? So how do we get essentially this set X? In general, essentially, a maximal independent set is generally a good solution for dominating sets. Not in terms of proof, but it is good. So as a set X, we take any inclusion maximal independent set in G delta to the 2 over 2. So inclusion maximal essentially means just maximal. Means that if you can include one vertex, include it. So you can essentially consider the maximal independent set in G. So the first thing is this one. By the definition of X, we know that it is a dominating set in G delta to the 2. Why? Because consider this vertex. This is the graph. So I want to say that it's the dominating set. Why is it dominating set? Because if there is this vertex, so these are the vertices that I already have in my maximal independence. If this vertex is not adjacent to anything, then I will include that one also in my independence set. Correct? So each vertex, either it should be in the set or one of its neighbors should be in the maximal independence set. Otherwise, I will just add this vertex as a new vertex to the. So by definition, an independent set is a dominating set. Good. And we are considering G delta to the 2. Because it's a dominating set in the G delta to the 2, then it is a 2 approximation. But we are not done. The main thing is that why the size of it is at most K? Because that's the very important thing that we need to talk about. So, of course, if the size is at most K, we are done. But what will happen if the size of this is not is greater than essentially K? So I want to say that if the size of this maximal independence set is greater than K, then optimum should be greater than delta. Why? So these are the vertices. Note that, here, these are the vertices in G delta to the 2. So just consider a ball around each of them of 2 delta around each of these guys. Good. So these are the independent set that you can essentially consider. So this is so each vertex essentially consider a ball of 2 delta first around it among these guys that I have done it. Good. But actually, so this is the first thing. So we know that each vertex, if you consider it, so what do we know about this ball of 2 delta? We know that each vertex should essentially fill in one of these balls. Correct? Now, what else do we know that? Now consider a ball of size delta around each of them. Good. Now, what will happen if you consider the balls of delta around it? So you want to say that these balls, from each of these balls, you need to select at least one vertex in the optimum. Why? Because if you don't do that, essentially, because these people essentially these are the maximal independent sets, and these are the delta. No, like essentially, no vertex can no vertex can dominate 2 of these balls. Why? Because if there's a vertex essentially here, I mean, the ball that it can cover essentially this one, uh, essentially it would be at most falls here. And that would be independent of the other. So that's the best thing. So essentially any vertex can go around 2 delta, and like the diameter that you can cover it is at most essentially 2 delta. So you can say that each of these guys, they need at least one vertex to cover it, and not like there is no one vertex can dominate essentially both of these balls. And that means that each of them needs at least one. So if the size is greater than k, essentially means that the optimum should be greater than the number of vertices should be greater k in the optimum. So this delta cannot be the correct optimum. So this gives essentially a simple 2 approximation for the problem. And you can, by a simple reduction from the dominating set problem, we can show that there is no 2 minus delta approximation for k center. So for k center, this is the best that you can get it, and 2 minus epsilon, of course, unless p not equal to mp, and you cannot get anything better than 2 minus epsilon. Now, there is another version of this problem that it is called the capacitated version. What is the capacitated version? Is that we want to have k centers, but each of these centers can have at most, I mean, they have some capacities, which is, again, happens a lot in the network design. You don't want to say, if there is like this guy, which is close to everyone, you don't want to send everyone to this person because it would be too much traffic. So this is the uniform version, is that each vertex here has the same capacity. And you want to see whether what is the optimal solution of size k. And of course, in that case, you just want to make sure that k times this uniform capacity C is greater than or equal to n, because otherwise it's not possible. Correct? So the k centers, each of them can serve C, essentially, people. So k times C should be greater than n. So as long as kc is greater than n, there is an optimum solution, and you want to find. Another version of that is that this is the uniform version. What about, there is a non-uniform version that each vertex in this essentially V that we are talking about, it has a different, potentially different capacity. Different vertices may have a different capacity. Still, you want to find the best case. And again, you need to check, this is an easy thing to check, that the k highest guy, the k highest capacity guy, the capacity of them, the sum of them should be greater than n. So that means that there is a feasible solution for us. And then find the optimal solution. Good. So what do we know about this problem?
Why is it only so if the sum of the top k people is greater than n?
Yeah. There's a solution.
Okay.
So all of these problems is important. Essentially, this is one of the other things in network design and others. Optimum, I mean, the feasibility solution should be easy, because if the feasibility is hard, then you cannot talk about approximation. Generally means that this problem is non-approximable. Any reasonable thing. So it should be at least one solution you can find it easily, and then say because there is one that I can find it, okay, there's the optimum that is the best among all. And then I want to try to approximate. So what do we know about this? What is the state of the art for this one? This is important because, good. So this is the state of the art essentially for this problem. So this is actually the paper that we had it. So when the capacities are when all the capacities are identical, a fixed approximation is known for the problem. Good. So if the capacities, all of them are the same, there is a fixed approximation essentially there. But this paper, this was the first paper that we had it with Marek Sigan and Samir Kuller, that shows that maybe I can just move it here for now. Yeah, so indeed, this is the Marek Sigan and Samir, that we give the first constant factor approximation for non-uniform case. So this is the non-uniform, which is important here. And we show also that, we write some natural linear program. That's actually one important thing. There was no linear program or natural linear program for these things. We can write a linear program and then we can run it. And when we show that, for example, the integrality gap of this linear program for uniform is 5, and for non-uniform is 7. So essentially, said that for uniform, again, integrality gap, it does not say about the hardness. We don't know. No hardness essentially known before, essentially. Or approximation actually is much worse than 7 here for the non-uniform case. But we show a lower bound of 7 for the LP. So that this LP, if you just want to use this LP, you cannot get better than 7. It's the integrality gap. But for uniform, we show it is essentially 5. And this was the first LP that we had it for this problem. That's a natural LP. You can write it down. So we show that, the hardness that we have it is that if there is 3 minus epsilon approximation for this problem, then P is equal to MP. So in terms of the hardness, we can get better than 3 is not possible. As I mentioned, for the case center itself, 2 is essentially the answer. But for this version, we can show essentially 3. It's also another thing that I want to say, that this is the hard capacity. Hard capacity is important. Hard capacity means that this is the maximum that you can do it. Generally, hard constraints means that you cannot violate. This is the maximum. There are soft capacity versions that essentially that you might be able to open, for example, more than one center at one location. Good. So if you want to, there are more people that are coming. For example, if in this case, if there's one vertex that decreases, so you may open a few centers here. These are generally means the soft capacity. Or like the capacities can be slightly more than the K essentially. So these are generally the soft version, which means some relaxation. So the general idea is either the capacities will be, you can essentially violate, or the number of them you can violate, or you may essentially open on one of these vertices more than one sentence. The most interesting thing, the hard part, is that you cannot violate the capacities, you cannot violate the numbers of the centers, and you cannot open more than one center in a vertex.
The 75 that you mentioned, are they lower bound or are they upper bound?
These are lower bound. So these are you cannot get better than 5 approximation using the SP that we write.
But do you get 5 approximation?
No, we get it much worse. And there are a few subsequent words that they are improving over the approximation.
But you also get upper bound.
Yeah, that is the whole thing. We give some constant lower bound, but that was much worse than that. We give, for the soft capacity, we give 11 approximations. But for the other one, we give a constant, but the constant is large, and there are some follow-up works that they are improving on the constant. I think maybe even 9 or something is now known essentially. I think Ola and others, they had some papers. Several people worked on this. So the non-uniform, there was no constant factor. But for identical capacities were there. Now, why did I emphasize so much on this one? Why do I emphasize so much about this one? So now consider the K-median. So what was the K-median? You want to minimize this. Instead of max, you just want to minimize the sum. Good. Big open problem. Capacitated K-median. Is there a constant factor approximation? That is a very big open problem. This is, again, you solve it, probably you can just write it the best paper apart. So this capacitated K-median, no constant factor approximation, even for uniform. So there, for K-center, we can get it. I mean, I will say the guess is that it should be possible, but we don't know any answer. In general, K-median algorithm are much harder than this other. This algorithm that I have mentioned is using that power graph, and this power graph plays the role on that LP as well when you write the LP, etc. for the problem. Here, I mean, the problem, the power graph is not that useful here, so you need to solve the actual. So the best algorithm for this problem, so what is the best for K-median? The best for K-median, I think it's currently is 2.66 or something like this. But for a long time, the best approximation for that was 3 plus epsilon. This, I think, it uses some LP essentially. But this is essentially is based on local search. I will talk about it. This is very important because this is the one that I presented. Local search algorithm generally is hard to analyze. This one that I'm presenting is probably the cleanest one that you can find. But you can see exactly how you can analyze a local search algorithm. And that is beautiful. And it's simplified again. I don't know any other such kind of simple algorithm as simple as this one that you can get anything. Here I will give in this one, the best one was 3 plus epsilon. That was a long, that was essentially, again, wide open. Can we improve better than 3 plus epsilon? Until there was some algorithm by, I think, 2.76, some LPL based, and then it was improved to 2.66. That's the best. But again, all of them are for uncapacitated version. Capacitated version, still we don't know it. Even constant factor. Okay, so what is the... So this one first, I want to give a 5 plus epsilon approximation. And then we will see how that. Good. So what is the algorithm? It's a very natural. What is the local search algorithm? Local search algorithm are like those heuristics, essentially. Start with, each solution, if you have any x which has size k, the cost of this solution would be this. What is the cost? I mean, go for each vertex, find the nearest vertex to that in this centers that I have. Again, I have a center, so it is k. Find the thing and then sum it up. So any solution, if I say x, who are my centers, you can tell me what is the cost of the solution. Because each one goes to the nearest. Good? Now, so just consider this algorithm. Start this on an arbitrary solution, x of size k. what do you do? If one center, so this is a start with arbitrary x. This is arbitrary x of size at most k. Okay. Then if a replacement helps, do it. That's it. So just start with x. And if you can switch one vertex outside with one vertex inside, you can switch it, and the cost goes down, just do that. Until you cannot do it. These are essentially the type of local search algorithm, this kind of greedy algorithm. Consider this one, and then if you can improve something, improve it. Otherwise, just stop it. That is the solution. This gives a 5 approximation. However, interestingly, this other algorithm this gives 5 approximation. The best, as I mentioned, the best before was this paper. This paper of Arya, Gargan, Kandekar, and Adam Emerson, Kamesh Monagula, and Pandit. They gave essentially 3 plus epsilon approximation. They just analyzed a little bit better than that. Instead of switching one to this, they essentially switch something in the order of 1 over epsilon vertices. Consider 1 over epsilon vertices. You can do that in local search. As long as it is constant, you can do that. A constant number of these vertices, all of them go out. A constant number of vertices, they come in. The same number. If it improves, just do it, and just do it as much as. So this is a general definition of essentially generalization of this local search algorithm. Instead of switching one, switch 1 over epsilon at a time. And as long as this epsilon, that's the thing that they get 3 plus epsilon. And as long as essentially this 1 over epsilon is constant, you can do that, because the number of this one, you will try all possible things. If one is better, then you will add. So that gives 3 plus epsilon. But I want to just give the 5 approximation that uses essentially more and becomes more complex.
Time is going to be something like
k to the n to the 1 over epsilon. Yes. I mean, you might be, yeah, generally it is like that. When you do it, then that will be good. So that's the thing. Now let me just go and see how can we prove this one, the 5 approximation. I think that's actually interesting, how you can do that. So this theorem essentially first is obtained by Arya et al. In their paper, the 5 approximation, but there's a paper by Gupta and Tang Wangston that is simpler proof, and that's the one that I'm presenting. That's a very nice. So, okay. So I want to say that and again, what was the algorithm? Consider 2 vertex V1 belongs to X, V2 does not belong to it. If the swap helps, just do that. In terms of cost, then do that. So here, note that, I mean, this is some algorithm that is just optimizing by itself. I need to somehow relate up to this. The general idea is that you need to find some kind of swaps. I know that when my algorithm ends, there is no swap. I need to find some carefully, essentially swaps that generally these swaps should be not overlapping. That I will say that because these swaps, I cannot do it. I can relate, and essentially I can, because these swaps are non-overlapping and I cannot improve it, I can essentially, using these swaps, I want to say that my solution somehow should be comparable to the optimum solution. That's essentially it. Again, it's beautiful actually. things. It's quite non-trivial to analyze this one. These are very easy algorithms to implement, but analyzing them is quite non-trivial. This is one of the, this one is essentially proof from the book. These are like a simple, so I say not trivial, but it's the proof from the book. Okay, what do I do that? So I need to find some swaps. That is the whole idea. I need to find some of the swaps. I think these swaps are essentially non-overlapping. I can write some equations for these swaps such that through these equations, I connect the cost of the optimum solution to the cost of my algorithm. That's the whole idea. So I need to find the swaps. Okay. So let X star be the set of K facilities chosen by the optimum solution. So these are essential. Always we say a star means opt. So this is X star, and we have X. Now, I want to define a mapping, nu, from X star to X. So I try to find, these are like essentially from X star, I want to map them to X. So how do I do that? This is a very natural mapping. From each X star in the optimum solution, I will map it, this new function, maps it to the closest vertex in X. I have a set of centers, so this is the optimum. And this is me, this is the alg. And for each of them, these are the centers that have, these are the same numbers. Correct? I will just see this mapping essentially. This is the nu essentially. For each one, I will say who is the closest to this guy. This will be mapped here. This guy will be mapped here. This guy will be mapped here. Maybe I will have some other guys that maybe this guy also maps it to here, but this guy there is no vertex. Now, this is the mapping nu, which is a natural thing for this problem. Now, first, I want to do that. So I want to say this is the lemma. There exists a set. So here, I want to get I want to find the swaps. But before that, let's do this. I define this new one. Now, say consider there is a set S of, essentially this set is from X times X star. Good. So this is one center that I have it. This is alg center. This is the other one is the opt center. There's a set of this one with this property. Each F star, each facility or center essentially the same, in the optimum appears in exactly one pair in S. Good. So this is the X star, correct? These guys, the optimum guys, at most appear one time. This is this kind of non-overlapping thing that I'm talking about, or at least limited overlapping. So each guy here, F star appears only one time here. Each F appears at most twice here. So here it is one time, here is two times. So if you have one facility here, it may appear twice here, but some facilities here, it just appear one time. F star. Now, this is important thing. For each F star, and for each F star belongs to X star, which is not equal to F star, this mapping nu does not map this vertex to S. So what's the meaning of that? It means that if I have F star, it cannot be the case that there is another F star 2 that the mapping maps this F star 2 to F. So essentially, it says some kind of, again, so there are some kind of, they are disjoint. It said that this is essentially intuitively say that if F and F star I have it, map of F star should be F. Maybe it is not the case. Good. So essentially, I want to have this one, the map of F star, like nu of N star be F. But even if not the case, like maybe the map of F star is not F. But I don't want anyone else the mapping of that becomes F. Does it make sense? So sometimes, as I mentioned, you try to get it essentially partition gets this kind of disjoint swap such that you can, because why? Because you want to sum at some point. This is, say this is the cost of my algorithm, and say this is the cost of optimum, and they can relate with some approximation factor. And this, for example, is this 2 and 1, or these are the one that they will come into approximation factors. Good. How can we create this one? This is actually easy to create these ones. So define these things. X star. So X star means those that then. So what are the X star? So consider essentially X. This guy, there are X0. Means that no one essentially, these are X0. No one is mapped to them from them. X1 are the one that exactly one person mapped to them. X, this is X2 plus, or those that they are more than essentially. At least 2 are mapped to this. So this is only 1, and there is no mapping. Good? What is that?
You start with the mapping.
We start with?
Nothing.
Yeah, we are starting with map new. This is the map. No. So from, I mean, since this map, no, essentially, I want to just say this. Good. So you just partition this one, say that this is the new. So, and again, these are all at this point are existential because we don't know opt essentially. I just want to say that there exists such kind of things essentially. Okay. So one important thing which is important, I know that x0 size of x0 should be greater than x of 2 plus. Because for one thing that I don't have this guy here, I need to, essentially x0, if I miss it, it should go to x2 essentially. And the degree of this guy is greater. If it was 2, you could say that essentially, you see, this x2 plus guys. Good. So this x2 plus guys, if these guys, they get their fair share, essentially 1 exactly. These guys, they get 0. This guy, they may get more than 2 or more. Of course, they get their fair share, but 1 extra. For anything that I will essentially here, I will miss, I don't have it. I need to have 1 person here, but maybe less than 1 because the degree of these guys can be more than. So, and there are n essentially because it's a mapping, there are n of these arrows. So you can see that the size of x star should be greater than or equal to the size of x2 plus. Good. Essentially, anything that we don't map it here, you need to map essentially here. This is some kind of double counting essentially. And these guys, they get a fair share, but anything that it is not here, it should go to one of these guys. And note that this is a partition. Each vertex should be in one of these. Yes, but you see, if this guy is missing, I will add this one. But I can have, like essentially, each of these guys can serve more than one of these guys. Like each of these guys, you see, each of these guys can serve more than one of these guys. That's the reason that I will get this. Otherwise, if the degree was 2, essentially, you could have the equality. But because the degree can be greater or equal to, that's the case that happens. Good. Now, what's the meaning of that? Essentially, that means this one. So, because the size of these two are equal, then we know that 2 times x star this is greater than x star plus this. This is just using these equations. And this x star plus this would be x minus x1, which is essentially x star minus nu minus 1 of x1. So I just replace essentially x1. So because their size are things, and these guys are the one that are the mapping it. Essentially, this is the one-to-one mapping. So this one is the one-to-one mapping. So this is essentially the main part. Now, to obtain f, how can I get it? It's a very natural way. For those x1 guys, I will just get f and nu minus 1 of f. So for this kind of mapping, I will just map them together. One-to-one mapping, I just map them together. Now, what about for the others? Who are the others? Now, okay, so I need to cover essentially the rest of x star, correct? Because that's the thing that I want to essentially create these things. So let's consider a star, which is x star minus this one. So these are the remaining guys. I will partition essentially all of these remaining guys. And so all the remaining guys, so some of these optimum guys have been already matched because they were just going to the same vertex when they had one-to-one mapping. Now for the rest, what do I do for the rest? Anything, I will just consider the rest of them. I will partition them into pairs. So U star, V star, and then U star, and so on and so forth. Good. Now, I just partition these guys, the remaining guys. Good. And then I will select a vertex from F. I will select a vertex F from X star. Then what do I do that? So I will consider a vertex F here. I will say, okay, this is the U star 1. So essentially, I will say F U star 1, and then F V star. So this is essentially for F1. Good. What does it happen? So essentially, I will do a very natural thing. I will consider so those mapping guys I just mapped to each other. Those that have not been mapped, I will just partition them into essentially 2 pairs. And then for each pair, I will take one center from F1, one in X1, and then I will map it. Then I will have it F1 U star and F1 V star. And I am fine. Why? Because of this equation. I knew that if I get it for each vertex, if I have 2 times X star, is enough to cover the rest of the facilities in Amt. Good. So 2 times X star is greater than the remaining people, and these are the remaining people. So essentially, I can cover all these guys with the vertices in X star, X0. What's that? I mean, arbitrarily. Just arbitrarily, because essentially, now what will happen essentially? You will see that each vertex from X star appears at most once, because once here and once here. Correct? Each vertex, each center in X star, either it will be in this one-to-one mapping, or here it will be mapped to one of them. But each vertex in X, it may appear twice. Why? Because this is a twice that it appears. because one vertex of X star here, I use it for two of them in the set.
Which
I mean, arbitrary again. Just consider just arbitrary things. The only thing I want that the numbers should essentially match. I know that twice times those guys that nobody mapped to them is enough to cover all these vertices. So each vertex, I will just bring it twice. Why do I do that? It seems stupid. It's not just stupid. Why? Because of this third property. Why do I do that? So in some sense, those vertices that they are, essentially these guys will not be used at all. Instead, I will just use double of these guys. So to create these pairs, I will just use this one once. I will use, this is once. This is double, this is zero. From these guys, I don't use in my pairs at
all. Oh, that's how you get a third property.
Exactly. So the issue is because of the third property. The third property is that if there is this one, then the mapping of these guys is not this F. This is trivial because no one is mapping to these guys. That's exactly because of this. Again, this seems, I mean, this is maybe more than enough for us, but that is good. So we got these things and we have this property. So we created this. Now that we have created F, now let's define this swap essentially. So this is essentially the swaps that, this set F would be the swap that I wanted to have. As I mentioned, they have some kind of overlapping, but very limited. Now let's see what can we do essentially. Good. Now we use essentially each swap in S in a non-improving. So we know that each swap, so if we had essentially in S, so in S, we have this F, essentially F star. These are facilities. So these are the swaps. I know that none of them are improving. Otherwise, I have done it. So I cannot swap any vertex. This F is my algorithm. This wins from optimum. I know that. I don't know what is optimum, but I know that I cannot do this improvement. Good. Because otherwise I have done it. Because this is a greedy algorithm. So I will consider this S essentially. This is S essentially. None of these, I mean, swaps in S should be possible. So this is a center. So what was the swap? You will, one of these vertices in my X, so this F belongs to X, this is X, correct? I cannot swap each of these my centers to, if I swap one of my centers inside X with some vertex outside, there is no improvement, correct? That was the definition of ending my algorithm.
But wait, you start with S. Wait. So you're saying S is going to...
So I will start with X arbitrary things, arbitrary set of K centers. If I can do some swap and improve it, then I will do that. I know that in the equilibrium case, when I settle down, I cannot do any more swaps.
Okay, so the S you're considering is for that X.
Exactly, for the final X. So when I reach to a place that X, this is essentially the part that my algorithm is essentially the output for the algorithm. And X star is the optimum solution that we don't know. At this point, I want to say that, okay, I want to do, at this point, I cannot do anything for X. So no swap should be helpful. So let's see what can we do in this case now. So what are the swaps that I'm considering the swaps in S? Good. Now, consider essentially this one of these vertices. So I have essentially this F and this is F star. So what would be a swap? So here in my solution, so these are X essentially. And this is, I mean, the rest of the guys. So this F that I'm considering it here, some people, they have been mapped to these guys, correct? To this F guy. I say that there is no swap is possible. So now consider the F star person. If I remove this F, I need to say how these vertices that are mapped, these other guys, they have mapped to other things. So nothing, no changes for them. But for these guys that they have mapped to F, I need to find a replacement. Good. How do I find the replacement? Let's essentially good. For a client V, each vertex V in this one, let OV be the cost of this. So this is the cost of serving this guy in the optimum. And AV is the cost of serving it on my algorithm. It means that, I mean, this connected to some guy in optimum, that's the distance there, and this is the distance in my solution. Now, let N star F star be those guys that they are essentially the, consider all this V that optimum maps them essentially to this guy. So essentially, this is my mapping. This is alg mapping. Phi is the alg mapping. Phi star is optimum mapping. Good. Now, again, you can just define N star of S star. So this is essentially, this is N of F, and these are guys that are mapped here, it will be N star of, but each vertex is some positive. So this is the main equation. For each swap F and F star, we have this property. The cost of this, if I swap this one, is at most sum of this plus sum of this. Good. So this is the lemma that I need to show essentially. And first I want to say that if I show that when I'm done. So what do we do? Just forget about this part because we know that it is impossible. It means that the cost should be greater than or equal to 0. I will sum it up over all vertices, essentially over all vertices. I'm summing up all these equations. What will happen? The thing that happens essentially is this. I will get, when I get sum it up over all things, from the sum of this, I will essentially get, this sum becomes essentially opt. Sum of all OVs, because all individual things, if you just individual contribution, if you sum it up, would be the opt essentially. Some of this part would be alg. Some of this part would be 2 times opt. However, I had this thing that each F can appear twice essentially. Because of that, this instead of this, each F may repeat twice. So then I will get 2 times that. So what do I get essentially? I will get it opt minus alg plus 4 opt is greater than or equal to 0. That means that essentially alg is less than 5 times opt. Is it clear? That's essentially the whole idea. As I mentioned, I created all of this to do that. Now, just say why we have this equation. These equations actually are easy to see. Let me just go through it fast and then we are done. Here. So we just need to do this one and then we are done. So since we are removing F, so as I mentioned, so here we are removing F and we are adding F star here, correct? We need to reassign all clients that were previously mapped to F. That is a client. These are all of this essentially in N of F. So I will map each client from N star F star to F star. So each of, if among these ones, some of them are essentially here, some of them, it might be essentially the intersection of this. If this vertex is the same vertex here, then map it just to F star. Good. Some of these guys, they have some intersection here. Just map them. So because this is essentially the people in the intersection of N star, F star, and those guys, just map them here. What about the remaining guys? The remaining guys, I will define this one. Let F star serving V. Okay, so what do we do in this case? I know that this vertex, so what do I do? This vertex V here, let me just use a different color here. So this vertex V here is mapped to some vertex F prime, actually. So F prime star. Good. Each vertex here, I mean, if it is not mapped to F star, it's mapped to some other optimum solution. Consider that one F prime star. Consider the closest facilities to this guy in my solution. So this would be essentially something, I will call it F prime. So each vertex, if it is either in the intersection, that I will just map it to that, to F star. If not, this vertex in the optimum somebody serves them. Correct? In optimum somebody serves them. No, that vertex itself should be served by one of my centers. So essentially, I will serve, so this guy is the optimum is served, and optimum, because this is one vertex in my, essentially in the instance, this guy should be served here. So I will just serve this guy. I will just serve this guy with this guy. Good. So that's essentially the mapping that I created. Now, what do I have? Then essentially you can say that how much, good. Now, this is the whole equation that we are done. Observe that for each V belongs to N star F star. So for each vertex here, we change it. So the cost is equal to exactly OV minus AV. So each vertex V belongs to here, the intersection of this one. Here, we paid AV. Here, we paid OV. So that's only the difference that we have. It is AV minus OV minus. Good. Now, this gives the first sum here. Now, what about the second sum? Now, for each vertex, which was not assigned to this one, this vertex V here, that was not there. It was assigned to F star here, and then from F star to here. We are using some triangle inequality here, essentially. We know that what is the difference. So the difference, before this guy was serving to, so what are the differences that I'm considering here? These are the things that I'm considering. So before I was serving it here, now I'm serving it here. I'm just writing some essentially triangle inequality and see the difference. So the difference between these guys, this is essentially the difference that I have it, is it goes essentially to here. So what is the difference? The difference would be the difference of this part minus this part. So I will just write it by triangle inequality. Now I'm just using the definition of no. So by the definition of no, I need that this essentially F hat, this guy was the closest to this F essentially. I can just replace this F star with F. I know that if I replace this one, because F hat was just an arbitrary thing, that was the optimum for me that I have done it. That's essentially by the definition of this, by the definition of S. Then I just replace this one with this formula. And then I will write again triangle inequality, because now I have these terms are coming out. And these two, I will just write it this one. And then I can just, again, by triangle inequality, I can relate it to this. And then essentially I am done. So you can say that the cost, the total cost that I'm changing, either this is the cost that I will pay for those guys in the intersection, or this is this additional cost that I'm paying for those guys which are not in the intersection. For this guy, as I mentioned, I will just use this triangle inequality and will write it down. A triangle inequality, whenever you are writing a factor, 2 appears. And that's the thing. As a result, I have these equations. I will sum it up over all things, and I am essentially done. So that's the thing, essentially, that it's 5 approximation. There is only one other catch that I wanted to mention here. So this algorithm, so this is one thing, is that this algorithm does not give a polynomial time algorithm. Since it does not show how fast you will improve a little bit at each time, but it might be not enough essentially. So you may go a little. This is like Nash equilibrium type of thing that you may go forever. It takes like essentially exponential time. However, it is possible to prove that if we consider the best swap possible, if at any time you consider the best swap, then we can actually obtain 5 plus epsilon approximation. So you are essentially losing a factor epsilon, but then you can get it in polynomial type. If you do that the best possible, then this is polynomial. And that's it. So I stop here.